It's a complex analysis day. Just making sure I got everything set up how I want it. Think I'm good. Okay. I think we'll just hop straight into the voice chat. Okay, so today we're talking about 3.3 and 3.5. 3.3 introduces the Laurent series. 3.5 is about singulated complex functions, which seem very connected to Laurent series. And I guess I'll just kind of scroll through and start. Trying to remember the issues that I had while reading this. Some of the bounds with these steps were very weird. Slim, thanks so much for the raid. Welcome in, everyone. Hope your stream was good. Bernie's just coming in. This is a reading group that I do on Tuesdays about complex analysis. We're talking about Laurent series today. Hey, Fembox. Hey, Poison Mouse. And hey, Cyber Secwiz? Okay. Like cyber security. Hey. Hope you're doing well. Hey, Rex. Poison Mouse keeps planning things for Thursday. He is known to do that and keep adding things on. I didn't message you about that, did I? I meant to, but I forgot. But yeah, you're welcome to join for that as far as I'm concerned. Mouse is having a friend of his join as well, apparently. Laurent? Oh, hey, Funlux.
Hey, Don, how are you?
I'm good. How about you?
Good. I'm a couple minutes late because Slim and Poison Mouse had an interesting problem they were working on. So.
No worries. Hey, Jasu.
I say Laurent. I don't know. It's French. Who knows? I don't speak French.
Well, I think me saying Laurent just really annoyed Jasu, so I think we should we should just like say it like that, just to mess with Jasu. More like Lauren, not like Laurent. I don't know. My pronunciation feels much more authentic. Chanel number 5. Okay. So there's a lot going on with 3.3 and 3.5. I had a hard time getting through it all, but I did manage to get through it. How about you?
Yeah. I read it. I read it all.
Okay.
You know what I've been doing? I've been reading it all, but I haven't been going through all the theorems. I mean, I've been reading the theorems, but I haven't been carefully reading the proofs.
Same. I've kind of
which is kind of skipping half the chapter because it feels like most of it is just lots and lots and lots of proofs.
Yeah, there's definitely some sections are super like theory heavy and some aren't. For a lot of these proofs, I kind of got stuck on one step and then I stopped with that proof.
I did find a couple typos in these sections.
Okay, because I couldn't tell if I just didn't understand it or if it was a typo. Like there were one or two spots where it just seemed wrong.
Yeah.
But yeah, I guess they start by just introducing the definition of a Laurent series, which is a very familiar like form. It looks like the Cauchy integral formula for a derivative, which I think it's supposed to be that because that's how it will, or like the Taylor series involves derivatives for the coefficient, so it kind of makes sense that the Laurent series would involve derivatives also. I think the only difference is that the Cauchy integral formula has an n factorial outside. That kind of makes sense for that cancels out. So I think it does at least.
I still don't have that integral formula memorized.
I just remember it looking basically the same as the regular integral formula, but you have an n+1 in the exponent in the denominator and then an nth derivative on the left-hand side. Are there pictures of Laurent series statement? I don't know what that means. Like I could take a screenshot of this if that's what you mean, but I don't know what else you would be referring to with that. HM3Z, in fact, thanks for the follow. Competitive programming? I've in general heard about it. I don't like follow or anything like that though. Geometric representation? Oh, I don't think I've seen that, no. Or if there is one, I haven't seen a geometric representation. Maybe visual complex analysis would have one. Hey, Dia. So there's a lot of things like the bounding by one where I tend to have issues. I don't remember, did I have an issue with this one? Maybe I didn't. Oh, you know what? I did have a slight issue, which is I think so I'm looking at the top of page 129 where they're bounding z minus z naught over zeta minus z naught, the magnitude of that. Z minus z naught, as far as I know, could equal R2 because the Laurent series does include R2 in the oh wait, maybe I answered my own question. C2. Maybe the Laurent series doesn't apply to the boundary. Never mind. It has to be analytic, including the boundary, but the series only goes for the like open region. Okay.
Wow.
Maybe that's it.
Yeah, they've been playing that trick a lot.
That also helps clarify why this note they put at the end of it is important, because I was wondering like what the note really meant, but I think that just answered the question. Where I guess they're saying that either way is fine for the analyticity of F. HM3Z, this is complex analysis. This is like an applied version of it, but it's complex analysis. Okay. I'm gonna keep scrolling through then. People are sleeping, Jed. CyberSec Wiz, thank you for the follow. Okay, and so they get to the two special cases. The bottom page 130. Yeah, no pride. So if f of z is just analytic in an entire disk, you just have a regular Taylor series, which I think is good to know. And then per B, I didn't quite understand what they meant by the f of z being analytic everywhere outside the circle R2. Like, it should also still be analytic between R1 and R2 also, I think. But I wasn't quite clear on that.
I guess it's just two different conditions.
I guess, but yeah, I know. I guess they make a point about that being a case where you only have negative terms of the series. But I'm still I wasn't quite sure how to interpret that case. Doesn't link the Wikipedia page as apparently having a geometric representation for a Laurent series. I assume he's talking about this. The red pick. Oh, this? I didn't think. Well, yeah, I mean, the book provided a figure like that. This wasn't, or this isn't the hard part, at least for me to understand, I don't think. Okay, what else was here? Laurent series are unique. They go through some examples of finding Laurent series depending on the domain.
I thought that 332 example was good.
Yeah, I found a problem like that as an example. We had to find it in a couple of different domains, which I think is going to be helpful to see also, because I feel like it's going to be tricky to actually do this.
Yeah, when I tried to do that example, the first time I did it, I came up with the wrong expansion, and I realized later what I'd done wrong. I hadn't been paying attention to the domains of each geometric series, because when you split it up into partial fractions, like each term has a different singular point, right? So you have to expand one of them like inwards, and you have to expand the other one outwards to get them to overlap in the annulus that you're looking at.
I'm not sure what you mean with the inwards and outwards thing, but like,
what do I mean? I mean, like, from the circle, you go in one case,
I see.
and from the circle you go out in the other case.
Yes.
And if you look at 3.330 there, 3.3.30, you can see that in one of them they factored a z out and they got 1 minus 1 over z. But in the other one they didn't factor a z out, they factored a 2 out.
Right.
And so, yeah, I guess the next line kind of explains it, because you have to keep track of where your mods are. You want mod z to be between 1 and 2. And let's see. Yeah, so the one I was screwing up was the second one, 1 over z minus 2, because I was just factoring out a z. I was like, oh, I'll just take out a z. But if you take out a z and you write it as 1 over 1 minus 2 over z, then you're not going in, you're not coming in from that boundary, you're going out to infinity. And you get a different series out of it.
Yeah. That'll be for like a different region.
Yeah.
So that's the part that's going to be, I think, tricky with doing this for ourselves.
Yeah. We just have to think. I think it helps to draw a picture. You just draw a picture and you see like each one, like, where are you trying to expand it? Where's the pole, or where's the singularity, and which way are you trying to expand it?
Yeah.
Or even just write out those little inequalities, with the absolute value of z. And that's what I ended up doing. I wrote down the two geometric series, and I was paying attention to which way z was going, if I wanted it to get bigger or smaller. So
Okay.
yeah, but I thought that was a good example.
Yeah. Proximity, nice, sounds good. And hey, Canis.
Oh, this is the mistake, by the way. That line where it says CN equals. So I think the second, it has -1 for n less than equal -1. I think it should also have a -1 over 2 to the n plus 1 for the greater than 0.
Yes, I noticed that too. I think I agree. Yeah.
Yeah, they just lost a negative sign there.
Oh wait, maybe the negative sign is built into the function definition. The C's are only concerned with what's inside the summation. Is that? Well, no, but then why is there the -1 on the first one?
Yeah, I think all the negatives have to show up in the
Yeah.
in the coefficients, in the C coefficients.
Okay, yeah, I think you're right. Yeah, that. Can we get Wolfram Alpha to actually do this? Just to be sure. Because
I don't know, maybe.
I think you're right.
That'd be cool.
1 over z1, or z minus 1, z minus 2. It's kind of doing it. I can't. What if I just put the word Laurent? Is it going to know what to do with this? Nope. Okay. If it can't do it, I don't know how to make it do it. Or it kind of was, but I didn't know how to interpret it. But it does seem like there needs to be a negative there because of the line like right before it with c sub n z to the n.
Yeah.
Okay. There was, for the one with tangent, there was one step that I just cannot understand for the life of me, which is once they on the denominator, they look at it as like as far as I can tell, they look at it like a geometric series where it's 1 minus and then like an entire series of things. This series down here is alternating, but suddenly it's not alternating up here. And I'm wondering if they only wrote out like the first, or they only really wrote out like 1 or 2 terms of the series, and so I wonder if they just didn't show the alternating part of it, or I really don't know how they went from one step to the other here.
Yeah.
3.3.27. Maybe I should.
Are you talking about like the plus that comes before the ... at the end of that line?
Yes.
Yeah, maybe they just are figuring they can put the minus sign in with the next term or something. I think you're right though. It should that last parentheses is going to be alternating, isn't it? Oh wait. Yeah, I don't know. I don't know what kind of magic they're playing there.
Because they did the same thing in 3.5 at least one more time, but I think a few times. And there they read it out more properly, where like you have the entire series or it's a summation of a series. So you have like the entire series plus the entire series squared plus the series cubed. It's a really weird thing. I wonder if they thought about that, but they only wrote out like the 1 in the u squared term. That's my best guess for what they did, but I don't really know.
What's that 3,327 that they're talking about there?
It's just a regular geometric series. 1 over 1 minus z is the sum of z to the n.
Okay, yeah. So they're just, yeah, that's what you said. They're doing a geometric. They're treating it like it's geometric.
Slim, that's how they define u. It's complex, I think, yeah. They're multiplying and dividing by the conjugate.
I don't think it's a conjugate. I think it's like a binomial expansion with a -1 power on it. I think that's what
Yeah.
they did. Whatever it is, I don't really like it.
Me neither.
Yeah, I don't really like it. I've seen that in another book where they found a series expansion for a tangent by like just dividing sine by cosine and just like basically doing long division of like, you know, of the Taylor
Oh,
series. That's just god awful.
that sounds terrible. Yeah, I don't know how you divide infinite series.
Just yeah, it's just god awful.
I guess you can
they
probably
only
do it for
did
a few
like
terms, but
yeah, they did like 3 terms and then they put a plus dot 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 and I'm thinking to myself, well, you know, this dot dot dot's not very illuminating to me because I don't know how to find, you know, the 7th term. I mean, I'd be here all day.
yeah.
But I guess if maybe what did they say? Find the other thing I didn't understand was how do you define the first 2 non-zero terms of a Laurent expansion?
How do you define the first 2 non-zero terms of a
Like where do you like when you're going from minus infinity to infinity, where do you start? Oh, I guess it means like in increase. I guess it means okay. I guess it means like from the negative infinity coefficient, and then you're coming along and going left to right, and finding the first 2 that are non-zero.
yeah.
Yeah, I guess that's what it means. Okay. Sorry, I should have realized that.
Okay. So that was all for 3.3. I guess for 3.5 we're learn about singular points, and this was I didn't realize that there was this much to singular points.
Yeah, they had a lot of different classifications.
Yeah. And it's a lot harder to figure out how we're supposed to find remember with the removable singularities, it's really intuitive in normal like single variable calculus because it's really easy to graph things. It's kind of annoying with complex numbers. You have to worry about like the multivariable limit existing. I know I was having like a more difficult time like imagining how we would kind of find and deal with those. I don't think it is equal to that expansion, Desmond. That's our issue. Or it doesn't seem like they did it right. Then we define poles as being specifically a discontinuity that comes from dividing by z minus some complex number to a power. And so calling the coefficient that goes with it the strength of the pole, like the word strength is kind of like evocative there. Like I feel like it means something, but they never really explain what that, like why we use the word strength there.
Yeah.
Like I wonder if you have like a fluid dynamics problem, if that would be like the magnitude of the flow from that sink or source, if that's what a singular point would be.
Oh yeah, maybe.
I know it's a geometric series, Destin. We're saying that they didn't use array. They don't
Yeah,
seem
they were
to
trying
have.
to use that. They were trying to use that geometric thing for this for a sign, wasn't it? Isn't that what they were trying to do?
I think so, yeah.
They took the Taylor series for sine, they factored out a z, and then wrote the rest as like 1 minus the rest, and then they tried to use the geometric formula to rewrite that. 1 over 1 minus all that business, and they wrote it as 1 plus all that. I don't know. It's just I don't get it.
Yeah, me neither.
Here's the next example where they did it right here on screen. Example 351. They're doing it again. I actually did this one out the long way. I found all the partial fractions and I got it down. And you do get those numbers they're talking about. You get a 1 and a 4 for the two strengths or whatever. A 1 and a -4.
Okay, yeah, so I just believed them because I couldn't, as like I don't think there's a way around doing the partial fractions for that, right? Like, and I just didn't want to do
Well,
the
I guess so.
I
I
just didn't
guess the
want to
way
do it.
around it is to use this approximation method that they've been doing with the geometric thing.
Uh
Yeah, but there's that -3 showing up from the cubic on the bottom there.
-3 in the second set of parentheses.
Yeah. Yep.
Okay. Yeah, I probably should have tried to get them in it for myself, but I could have wolframed out uploaded it, I guess, but yeah, that one just took them at their word. Oh, is this another one where? Okay, yeah,
Oh,
this is where they do it like properly, or as far as I can tell.
I guess when you look at, okay, so looking at this example, they're showing it more explicitly what they're doing. But if you imagine like throwing out that square term and throwing out everything in the first term except for in the first parentheses except for the first term, then you can kind of see how they got away with what they said in the other example, I guess.
Yeah, like I guess you would have to make sure that like minus z to the fourth over 5 factorial is going to be less than the z to the fourth term you get from the second set of parentheses. Would that be true? Z to the 4 over 120 negative plus z to the 4 over 36. So yeah, okay, I guess it would turn positive. And you may or may not get alternation.
What's new or better with Laurent series? Well, one thing I learned today is that you can use a Laurent series to expand around a pole. And I don't think you can do that with a power series.
Yeah, I think Taylor series only work when you're analytic everywhere in the domain.
Yeah.
And there are some cases where Laurent series fail, but they're way more exotic. or not necessarily exotic, but they're like, you know, the Laurent series work in way more situations than Taylor series do. In proximity, I see what you're saying, Sonic Tingle. I'm not sure what you mean with that question. Okay, and so it is kind of interesting that in order to describe the poles of the function they originally gave, you have to find the Laurent series in order to do that.
I mean, when I looked at that function, I just figured, okay, it's z plus 1 on the top, and on the bottom you got a z and you got a sine z, and the sine z is going to have poles at multiples of pi, right? Like 0 and then plus minus pi and plus minus 2 pi. So I figured there'd be a double pole at z equals 0, but they didn't say anything about all the poles at like pi and minus pi and all the other ones.
Right. That is weird.
I felt like they didn't really finish the question.
And actually, yeah, you a second order pole at z equals 0, but there is also a 1 over z term that would just be a first order. So it's kind of, I guess you just always take the higher one.
Yeah, I guess.
I wonder if this series is only valid in a certain domain, because surely if, like, we can find more places where it won't be analytic.
Oh, that's a good point. Maybe they meant for us to expand it around z equals 0, right? And maybe we couldn't go out as far as like pi or minus pi.
Maybe like
I'm not sure.
like maybe they implicitly did it around the unit circle or something, because the formula for the coefficients does involve a contour integral, so you have to draw the contour somewhere. Maybe. Uh, I kind of want to quickly Google that, because that does seem like it'd be helpful to have clarity on. I'm not seeing the exact thing though. Yeah, oh well. In the very next example for tangent, we do get infinitely many poles.
That's weird.
And they just simply say that there's strength 1 before even finding any series. I guess because maybe they're using the real Taylor series, and they're only talking about the real axis there. Hmm. Wait, so at the very beginning they say FC has simple poles with strength +1 at those points, but at the end they say it's simple with strength -1 at all these points. Excuse me? I didn't even see that before. What are you doing to me, book?
Hmm.
This m is also just an integer though, so I don't see what the difference is. Okay, I don't know what's up with that. Oh, yeah, the relationship with branch cuts is super weird. Um, I think it should be the same, Decim, as far as I can tell. But they did kind of tactically choose this example, so the branch point is not the same as the singularity. And they address the other case like later on. Sample 3.5.5. I feel like I should know this already. I got a little bit stuck on justifying exactly why 0 is a branch point for square root of z. Like, I realize that it is multi-valued because of the plus or minus one thing, but like I was trying to do the argument with making a circle around the branch point and getting to a different value, and I couldn't really figure that out for square root z. For log, it's a lot more obvious to me. You know, maybe they do make that argument, and I just forgot it back in chapter 1 or 2.
Maybe the square root of, well, the square root of 0 is 0. No, that's not what I meant to say. The square root of 1 is 1. But then if you go around 360 degrees and come to it from below, you could kind of say the square root of 1 was negative 1, I guess. Because both 1 and negative 1 can square to give us 1. So I guess if you go around 0, you can get two different. Like as you go around 360 degrees, I guess you would get to a second value of square root.
Okay, yeah, I just remember that they actually do read this out in section 2.2. I'm just trying to like quickly reread it. Value z.
I don't know what a ramified point is. Yeah, what the heck's a branch point? What the heck is the definition of a branch point? Did they talk about Riemann surfaces in this book?
I don't remember
I
learning
know
about that term.
I know we saw that picture for we saw a picture. I don't know if it was for logarithm or for the exponential or what it was for, but there was like the parking garage. I always call it the parking garage. And they did
Oh,
have a picture
yes.
of that in the book somewhere.
We didn't go through it, but section 2.3, we looked at the picture.
Yeah. Oh, that's Riemann surfaces. Okay. Yeah, they did talk about that.
Okay, I'll have to go back through this for the square root, but that's not the important part of what they're saying in that example.
For every circle centered at the point, you get a different value if you go once around the circle. Yeah.
Yeah, it's obvious to me with log why that happens. I've never tried to apply the argument to anything else, so I should learn it in more context.
Well, you know how in real numbers, when we write square root of 16, we write the symbol square root, with the radical sign with the 16 under it. We define that to be 4, right? It's not plus or minus 4. If you want it to be plus or minus 4, you have to put a plus or minus in front of it.
Yeah.
But if you have the equation x squared equals 16, that one has 2 answers. So yeah, where am I going with that? So if you have a point on the real axis in the complex plane, like at 1, and you want to take the square root of that, when you want to take z to the 1/2, I guess that they call it a multi-valued function, right? There's 2 different things you could have, 2 different solutions to that equation.
Yeah, I get that part. It's just like the making a circle argument that I really struggle with.
Yeah, you got to think of the picture in terms of that Riemann surface, like you're going up a ramp or something, So as you go around from 0 to 1, as you circle around the unit circle from 1,
I imagine it'd be a different shape than the parking garage that you get with the logarithm.
Yeah, it is a different shape. I've seen the picture of it. It looks like, instead of going an infinite number of circles, it's like you have 2 discs, and they cut through each other at that where the branch cut is. It's like you have 2. It's like you have 2 circles, and they intersect each other through the branch cut.
I don't know. Drawing the circle function is not continuous. That, I think, helps Slim. Because I feel like if you... well, yeah, I don't know. I don't know. Oh, did you find one?
Maybe. If you click on that, there's a bunch of images. The second one is the one I'm thinking of.
Ooh.
Yeah, see that second one there? So
that's kind of wild.
So what does that mean? When you're on the red, the square root is -1, and when you're on the blue, the square root is +1. And so you go around you go around twice to get back to 1 again. Does that make sense?
Yeah.
Or just say the blue is the positive square root and the red is the negative square root.
Okay. That's a nice visualization. Oh, okay. There you go. Okay, yeah, Slim. Because once you do the square root of that, you have to go around twice as much to get back to the 2 pi. Okay. Where is Zach? Yeah. Okay, so there's another thing with this example problem where at the very end, if you take the positive branch, they say that t equals 0 is a removable singularity. And I think we found that because in the series, there's no t's in the denominator. So we can actually evaluate it to be 1/2. They didn't say that explicitly, but I assume that's not a removable singularity for the minus branch because there is a pole. But like that's why I felt a little bit uncomfortable with like the removable singularity thing, because we're just like taking it from the series rather than taking a limit, which is what the argument that I'm used to.
Yeah.
That I guess makes sense. I guess you're taking the limit of the series. Maybe that's the argument. Because the series is equal to the function. And then we get into essential singular points. Singular points that you just can't live without. And so I did think it was pretty interesting that like that's where I realized like, oh, so these are the ones that give you infinitely many negative terms, whereas the other ones they showed before all had a finite number.
Oh. Okay. I hadn't realized that.
Um but yeah, it gets a little wacky with the example that they show. And they
Gosh, some of this is not looking for. I swore I had sworn I'd read all this, but some of this you're showing me on screen right now, it's not familiar. I don't know.
oh,
I must have skipped a couple pages by accident.
okay. Well, basically they dive into the example e to the 1 over z for an essential singular point, and they
Mhm.
make an argument that around z equals 0, it takes every single value infinitely often, and that's what makes it an
Mm.
essential singularity. So you can't like pin it down to one value, I guess. I'm not sure.
Oh, I wonder if I got a different book.
Oh, I hope I'm using the right version of the book too. uh
Yeah, wait a second. I'm on page 149, and my page 149 looks different to your page 149. Wait a
Really,
second.
maybe it's not even the first time that we've had a difference in pages, right?
Oh no, no, wait a second. No, maybe it's the same. Theorem 351. No, maybe it's the same.
um
No, I think it was my bad. I don't know how I missed a couple pages.
okay. Happy birthday, Ved, and a Papadoria. Thank you for the analytic continuation of my name. I am getting slightly scared that I've been using the wrong version of the book, because I didn't realize there are two. I want to quickly verify what the syllabus for the book actually is. Uh, 5, 6, 7.
I've been going back and forth. I was reading this book, but I was reading my Kreisig textbook too.
Introduction and applications.
Yeah, that
Cambridge.
cover is the one I got.
Okay, I think I have it. They don't say the actual ISBN, but it does match what the syllabus is saying as best it can. So one from 2003, one from 2023. Oh, really? You like the older one more? This is 2003. Okay, well, I was just at the ISBN, but as far as I can tell, this is the right book. Trying to validate a limit that popped up in your friend's physics class. Ooh, nice. If it's physics, just throw a Taylor series at it. That's my advice.
I just approximated with the first two terms.
Yeah, exactly. So yeah, I didn't follow the entire argument they made here, but the conclusion.
What are they trying to say? They're trying to say that zero is a essential singularity for
e to the 1 over z, right?
e to the 1 over z. Okay.
That I think I've heard of that site. I'm using this PDF for a reason though. Oh, Papadori, that can land you in trouble. Physics usually gets they use Taylor series for a reason in physics. Just hard limits. And so they switch it into polar coordinates, and to make the analysis simpler, they look at just certain values of r. But it was like an unusual choice of a circle to look at, so I didn't quite follow everything, but they end by saying that the function takes on all non-zero complex values with a certain modulus infinitely often. Am I married? No. And that I guess it has something to do with tangent is going to diverge as vice for certain values of theta. But I don't know. They mentioned Picard's theorem, which for soon I always thought that was a differential equations thing. Maybe it's also differential equations. But I thought it was kind of funny because then they said that proof is too hard though, so we'll show a similar one from wire stress. Page 120. That looks very similar. I don't know what you want me to get from this, but that exists. What else do they do here?
Meromorphic functions. That's what Sasha was talking about last week.
Oh, yeah.
I think, right? I think
Someone mentioned it at some point. I remember like skipping ahead to this page somewhere. Uh, it's kind of like a Merrill doesn't have to be polynomials though. It just says a ratio of entire function, so it could be like e to the z over sine z or something too. I would think.
yeah.
But I guess they're good to know about because all of their poles have to be singular points, or its singular points are all poles. Yes, this part of the chapter kind of dragged on, but then they start talking about branch points, and they call branch cuts like a sort of continuous singularity, like a singular curve, which I kind of had a hard time understanding that. I get how it's like a sudden jump, I guess, but it's kind of weird to think about them in that sense. My username is a meromorphic function because of gamma. Whoa. And then they talk about log z over z, which has both a branch point and a pole, or some kind of singularity at z equals 0.
Yeah, there's lots of different types of singularities, and I don't think I know all the terminology yet.
Me neither. Um. Oh my god. Yeah. I forgot how long this one was. I they talk about tangent of 1 over z though as having infinitely many singularities close to 0. I thought that was pretty
Yeah.
cool. And that one just has no Laurent series
Mhm.
around 0 at least.
It's just too evil of a function. You can't really build a nice series of it.
Yeah. Then you can have jump discontinuities. Cluster points should be known. I've heard of cluster points as like not with singularities, but as a more general thing. Like a cluster point of a set is a point where every neighborhood has either 1 point or infinitely many points. I forget which one, but it's something like a limit, but it doesn't have to be unique. Like you have multiple cluster points. Okay, and then they end by talking about analytic continuations. So you have to be careful with analytic continuations if there's branch cuts.
That was a cool example with the logarithm there.
Yeah.
With the 3 little regions of where theta was going to be able to live.
Mm-hmm.
I thought of that one again in terms of like the parking garage graph,
Yeah, I think that's the way to do it.
So you could see that as you went from like the theta 1 to the theta 2, you could be on the same level. From theta 2 to theta 3, you could be on the same level. But if you went all the way around from 1 to 2 to 3 and you're in quadrant 1, well, now you're upstairs. You've gone up a whole level.
Mm-hmm.
Yeah. Where did I see the word monodromy recently?
I don't know. It's another one of those weird words I never heard of that get used in math though. Hey, Phobos.
Drum cat.
Yep,
Always welcome.
it is.
Drum cat is watching. It should say drum cat is judging.
Yeah, it is a pretty judgmental cat.
He's looking into my soul and saying, "Why don't you understand Laurent series?"
It's just a geometric series. What's so hard? Um. Oh, so we're just talking about analytic continuations of functions and how they can get tricky if branch cuts are involved. And we just got to a point, or I scrolled down to a point where analytic continuations are impossible if there's something called a natural barrier or boundary.
Oh yeah, this sum of z to the 2 to the n. This was interesting. I just read this like an hour ago.
Yeah, so this one is good for magnitude z less than 1. But outside of 1, you're just out of luck. And they show it in a very unique way that where they figure out a functional equation that's helpful. But they show that it basically has infinitely many poles, I think. Or singularities. Oh yeah, they show that the entire unit circle is a singularity. If there was just a little patch that wasn't, you could like make a contour through it and figure out the analytic continuation outside the unit circle, but you just can't.
Well, maybe we could say the singular points are like dents on that unit circle.
Ooh, probably, yeah. So that's pretty cool. Okay, want to get to some questions then?
Yeah, time to get killed by some problems.
Okay, the schedule link is posted. From section 3.3, the first one I grabbed was number 2. Natisha, I'm not doing math help right this instant. The quick answer though is that area is 2-dimensional, volume is 3-dimensional. They're not quite the same thing. You can have the area of a square or the volume of a cube. basically. Developed your complex analysis studies, made a couple of friends for life from that time. Ooh, nice. Destin.
Okay, I got confidence about this one. This one looks all right.
Yeah. I guess we should partial fractions it.
Yeah, I love it.
I'm glad that one of us likes partial fractions at least. Um,
Both 1/2a.
oh, I would be very happy to just take an answer and not actually solve this.
Well, we better solve it.
Oh, okay. Oh wait, no, I'm doing that wrong. Okay. Um, a minus b equals 1. A plus b is 0. Okay, so that means a plus a is 1. So a is a half. B is minus a half. Wait, I did this wrong.
Looks okay to me.
I forgot the small a's.
Oh, well, you can throw them out, I guess.
Oh, they do get thrown out. That's weird. Okay. Okay, so half times 1 over a minus z minus a half times 1 over a plus z. Okay. So first off, for z less than a, they want us to do see now here I just want to factor an a out from each of these because I want there to be a 1 for these. Ooh.
You need a 1, yeah, and you need the 1 on the right in the right spot. So a good way to think about it, if we look at part A up here, we can change this into 1 is something is less than 1, right? We want to rewrite this so it looks like something is less than 1.
So z divided by a is less than 1?
We would have to divide both sides by a here.
Okay.
Does that sound right? That's what we want, right? We want something to be inside the unit circle so that the geometric thing can work.
I'll just see how this looks and then hey Storm, this is the question here. Nitish, yeah. I don't like working on those questions. I think this is fine now to apply the series.
Yeah, I think it looks good.
Um, hey Lucas. Pretty good. Just struggling with a complex series. So wait, the singularities are at plus and minus a. Yeah, we are just analytic everywhere inside a and everywhere. Huh. Yeah, it is, Lucas. Yeah, Destin and I have a point where this question... Like, isn't it more interesting if we're enclosing in a singular point?
Well, that's what I'm noticing, right? Right? We're just getting like what looks like a regular power series. We're not getting any negative exponents. Does that matter? If it says a Laurent series, do you need to have negative exponents on your Z?
Oh, I
I
guess
feel like,
not. Like, I guess every Taylor series is a Laurent series.
right, because they said Laurent goes from instead of 0 to infinity, it's like minus infinity to infinity.
Yeah, I think what we're going to want to do for part B then is factor a Z out from each of these and look
Yeah,
at the
for
other
for
side.
part B, we're gonna have to do it the other way. The Z's will be on the bottom instead of on the top.
I would like to simplify these into one summation because I feel like we're going to get cancellations.
Yeah, every other one's gonna cancel, isn't it?
Um, Lucas, sine of I is completely fine in complex number land. Do, do, do. So what actually the odd terms are canceling? It's like the ones are canceling.
Yeah, they are. So we could just get 1 over A times, yeah, Z over A, and then Z
Yeah.
cubed over A cubed.
Uh, yeah.
Cool.
Okay. And then that's for part A. For part B, snake over here.
I wonder if we could have cheated our way through it quicker just by using some kind of known series that we already knew.
Oh, maybe.
Yeah.
It does seem suspiciously like cinch or something. It's not quite. I was thinking of like series that only have odd terms. Um, so this time we'll factor a z times 1 over 1 minus a over z. And a over z is now less than 1.
Yeah.
Okay, and then it should be pretty similar from here.
Yeah.
Do, do, do. N minus, oh my gosh. Is this going to be the even terms, I wonder? We're gonna get the same cancellations. The signs are all the same, right?
I think we will get the same cancellations.
Okay. So, in the spirit of being lazy and not writing out the first few terms, I'm just gonna say that we get the odds.
Yeah, because if you look at the function they gave us, it is odd, isn't it? I mean, if you change z to minus z, it negates it.
Oh.
So we should get.
Yeah. Okay, they should both be. Well, I guess we're gonna get even powers of z, ironically, for the outside part.
Really?
Because we have a z on the outside.
Okay.
I'm dropping a 2. No, I'm not dropping a 2. So far, we got a 2 once we combine them.
Yeah.
So a to the 2n plus 1 over z to the 2n plus 2. Weird.
It doesn't feel right to. I'm just going to check this.
It's an even number.
Oh, no answers in the book for this one?
No.
Oh, that's fine. Could we quickly check this? What if we plug in like z equals 2a? Let's let z equal 2a. What should we get? We should get 2a over negative 3a squared. So we should get negative 2 over 3a. Is that right? Well, this is not giving us anything negative.
Oh wait, I did flip the. I flipped. Wait. Oh, I'm looking at the wrong set of work.
Yeah, I was checking part B. If it's 2a, we will use part B.
Yeah. A to the 2n plus 2. 1 over a.
Oh, wait. Is there a mistake?
That does seem like an issue. We're not getting anything negative. Did I mess up? Did I miscopy down? Something? Oh no.
What?
I just resized my window. By accident.
Something's not right here because if I plug in 2a into the given problem before we used any kind of series. If I do f of 2a, I'm going to get something negative. And our Lorentz series doesn't have any negative terms left in it. That's confusing. Well, that sucks. I thought this would be an easy one.
I'm really confused.
Yeah, me too. Let me look at this partial fraction. I was happy with it.
Wait, what from is saying both are negative in the partial fractions?
Really?
How is that possible? That can't... That... Did I mess up very early? A minus z, a plus z.
Oh, wait a second. I think I do see a mistake here. Yeah. When you pulled out a z from the very first partial fraction, we're going to get -1 plus a over z. Yeah, there's a sign mistake here. We need a negative here, I think.
Wait, where's here?
Just where you did b,
Okay.
I think this needs a negative.
It does?
Just double check me. Yeah, it does, because the a is flipped around, right? If you want to put
Oh,
the
it's
one first, you got
-1.
it.
Okay. Dang. Okay, maybe the...
Well, that makes more sense because we'll probably get something odd again now, because I wanted it to be odd.
Yeah.
I mean, I don't care if the z's are upstairs or downstairs; they should be odd, shouldn't they?
Probably.
I think
uh...
the exponents should be odd, I think.
So... Now how... Okay. Well, I guess I shouldn't be lazy with, not writing out the first few terms. Because I'm not going to be able to figure this out mentally. Okay, so now the odd terms will cancel, and that's good because we still have the z out front to make it even. Or whatever it is. We're going to get only even terms that'll turn odd once we bring the 1 over z in.
Cool.
And we do have a negative out front.
And a 2.
Yes. So let's just get rid of the 2 there. Thank you.
Yeah.
Okay.
So let's see. If you compare that with what we got for the part A, actually, if we bring that A inside, we get the reciprocal almost, don't we?
Oh yeah,
Wait a
there's
second.
2 extra A's in the first one.
Oh, we'd get Z to the 2n plus 1 over A to the 2n plus 2 over here, wouldn't we? Okay.
Huh, that's weird.
Okay.
Hey, beware. It's a summation. It's Greek letter sigma. It's kind of hard to explain, but it means you sum things up, add them.
Now, if I just check something, check Z equals 2A, I'd get negative sum A to the 2n over 2 to the 2n plus 1A. So I could cancel those. So I'd get 1A on the bottom. And what's the sum of 1 over 2 to the 2n plus 1?
You pull a 1/2 out front, and then make it a 1/4, I guess. Like 1/4 to the end.
Yeah. What's the sum of 1 over 4 to the n? A quarter over a quarter over 1 minus a quarter, right? A third. Is it a third?
1 over 1 minus a quarter. Isn't that gonna be 4/3?
1 over 1 minus 4 a quarter is 4/3. Okay. So we get minus 1 over A times a half times, you said 4/3
Yeah.
equals negative 2/3, 2 over 3A. That's exactly what I wanted. Yeah, because that's what
Okay.
you get if you just plug 2A into the original thing they gave us.
Nice.
Good.
Okay.
All right. I think we got it this time.
Yeah. I only pulled one other from this chapter. I'll show it, but honestly, we could also just skip it because it's pretty similar to the one that we just did. Now that I look at it again. So the only thing that's ever is now we have
Yeah,
3 different regions,
it's
but
similar.
I think the only thing that's going to change
Yeah.
is whether you factor out like a Z or not. I guess like
Yeah.
yeah. Honestly, I feel like we can probably skip this one in favor of just going on to the next section.
Yeah, if you want. I think we know how to do it. It's kind
Yeah.
of similar to that one we talked about from the chapter.
Yeah.
Yeah.
So this one, I think I just said 4 from these. We've read a bunch of them, but the ones that seemed interesting to me were A, C, F, and G. Or that seemed like distinct and interesting enough.
Oh, look at this. They have the list of all the singularities: removable, pole and order, essential, branch, cluster, natural barrier, and then they say etc. What is there more? Is there more? Oh, there wasn't there the jump. There was a jump
Yeah.
as well they talked about.
Mm-hmm.
Oh man. All right.
Give the nature. Include the point at infinity. Okay.
Oh, yeah.
So they said that the only things that are analytic at infinity are constant functions. I remember that. Okay, see ya, beware.
Could we do part A as just write it as a Taylor series?
That's probably the play, yeah.
Yeah, because we know E is entire. E to the Z, I mean.
Yeah. Your name went down to unknown reasons related to the chupacabras? Probably. The one can just remove the first term from that series. So we end up with z to the 2n minus 2 over n factorial. So this thing has no z. Oh, wait. It has one z in the denominator. When n equals 1. Wait. No, I'm sorry. I don't know how math works. The first term is just 1. Okay.
I think the first term is 1 over Z. No, it's not, is it? The first term is 1. Oh, wait a second then. Are there no singularities? Oh, we have to go to infinity, maybe. Is that all we got to do?
Yeah, I think we only get a singularity at infinity then, weirdly enough.
Yeah. Must be.
Uh, Now what type of singularity is this? I think so.
Don't we have to plug in, like, change Z to 1 over T?
Yes. And I think we're gonna get removable because the 1 stays the same. And if we go take the, because we're interested in t going to 0. So all these terms over here are gonna go away and we get just a 1. Or is that, does that mean it's not a singularity?
Well, wait, no, these don't go away, right? All these things get crazy.
Oh wait, you're right. Yeah, it's the opposite.
Well, doesn't that mean this would be an essential singularity?
Hmm.
Because we're going to have 1 over every even power of T. Like, it's like an infinite strength, an infinite pole or something, pole of infinite order, if there is such a thing.
Oh, Lou Bird. It matches. Huh. Thank you, Collar Cone. Where was that? Where did they do that in the book? Okay, yeah, here. It does match their definition of a pole.
Yeah, but wait,
Huh.
look at that. Look at that carefully. It says it's a pole if the numerator is non-zero at the point that we're interested in.
We're talking about infinity, right?
Oh, no, I think we're talking about 0 right now. If we're thinking of z equals 0,
We could go back to the original one though. Uh, how do we see that in the Laurent expansion though? Because we don't. Oh wait, or maybe we were to. Huh. B of z not equal to 0. I mean, I think we can't do the 1 over t thing if we're going to do that.
yeah, I didn't really want to do the 1 over 2t thing, but yeah, because I mean, if we let z equal 0, we do get 0 over 0, right? We got 0 on the top and the bottom.
Yeah.
It must be removable then, right? Isn't that what it would mean to be a removable discontinuity? Because when you expanded it out and rewrote it, we got this thing that looks like a very nice polynomial, right? I mean, we didn't see any problem with 0 anymore, so it must have been removable.
Oh, the pole. Oh, yeah, because we think we have a pole at z equals 0. Or we kind of do. Okay, yeah, I like that. Because I was doing the argument with t going to 0, but that's not what we want.
I guess that's a different.
It's
Maybe
a
that's a
different
different
story.
case.
Yeah.
It's a different story, right?
Okay, so removable at z equals 0. That's how we're interpreting it, Slim? Uh, and then for infinity, we kind of get infinity. I don't know that necessarily means essential, though. Maybe it does. They do say that for an essential singularity, you get a full Laurent series in the sense that you have infinitely many negative terms. Well, it goes off to infinity in both directions. Are they going off to infinity in one direction? Where were they talking about entire functions? Here it is.
What was the definition of an isolated singularity again?
You can find a neighborhood with around that point with no other singular points.
Yeah. Okay.
So I guess I should say z is isolated, or 0 is isolated. Uh, entire functions have isolated poles or essential singularities at infinity. They famished. The name of it is in the pin. Here, I can just show it for a second.
Tyler Cohn says you can cover the singularity to get rid of the pole if it's meromorphic.
Hey, Armand.
Yeah, if you think of writing out e to the z squared as a Taylor series and subtracting 1, once you subtract 1, everything else has z squared in it, doesn't it? And then you can factor out that z squared from the numerator. And then you've got z squared times your polynomial divided by z squared, and it's kind of like you cancel them out. It's like canceling out 0 over 0 when you're trying to take the limit of in calculus 1, right? You're trying to take the limit of a function when it's not defined at a point, and you say, well, if the numerator and denominator are both 0, then sometimes the zeros can cancel like that. And I think that is what they call like a removable discontinuity. If you graph the function, sometimes it's nice and continuous, but there's like a little white circle in the middle of it.
Yeah.
Okay. Yeah, I was just rambling about what we'd already done.
The thing so yeah, color code. The thing that I still don't know about is infinity, because they do want us to talk about that too.
It feels like as z goes to infinity, the numerator gets bigger a lot quicker than the denominator, doesn't it?
Mm-hmm. Okay, so we did that, but then as t goes to 0, you just get infinity, and now we don't know how to interpret that. Like, is that essential, or is it I feel like it should be a pole, but I don't know like what's the order of that pole, because we can always get higher order negative t's.
Yeah, the t's just keep going, don't they?
Laurent series is infinite, many coefficient. Okay.
I'm going to guess it's essential. It just
So
feels very essential.
Okay, color cone agrees. I don't know, for a reason that doesn't quite sit right with me, but I should get used to it.
Okay, wait a second though. Why? The Laurent series has infinitely many coefficients in the negative direction. Is that what? Oh, that's right. It did say that somewhere in the chapter. And you
Yeah,
pointed that out to me, Don. Remember? And I said, "Oh, that's good to know." I don't think I'd read that.
I,
Oh,
what I was getting stuck on is that it said the series goes from negative infinity to plus infinity, and we didn't go to plus infinity. We only went to negative. But I guess that's still okay. Here it is, page 148, the top of it is where they say it. That is series for negative n does not terminate. Maybe I should have read that piece of the sentence. Okay. I'm okay with that.
no matter how big you choose capital N, you can find negative coefficients further out.
Okay, yeah.
Okay.
Fair.
That's good. I feel like I learned something just now.
Meromorphic function defined in the whole C. The only possible example are rational function ratios of polynomials. Oh, because of power series or Laurent series? Oh, cool. Oh god, I'm just looking at F again. Why did I choose F? But I chose C first. E to the tan Z.
Oh, e to the tan Z.
Okay, what's up with that?
Well, e plays nice, but tangent's not nice when sine is 0. Cosine is 0. So we got to make sure cosine's not 0, I guess.
Oh yeah, true. The E part will never cause issues. So does that mean it's just gonna be the same as for tangent?
So cosine is 0 at what? Odd multiples of pi over 2.
Right. Yeah, I guess maybe it's just the same as tangent. That is one primitive manifestation of Sayre's famous Gaga theorem. I feel like I've heard of that. Does that have to do with function composition? Uh, it's an amazing link. I don't know. Yeah, I shouldn't read this. That looks too complicated. Okay, so I guess yeah, we're just gonna say these are poles, right? What was the conclusion? Simple poles with strength 1.
Will they still be poles once you like plug them in the exponent of e like this?
Should we think about the power series of this, of E? Ugh. I don't know if this is a good route to go down, but oh, would we have to do like a geometric series trick with this thing? Maybe. I kind of hope not. Cosine should be the evens.
Oh, I see what you're doing.
Well, the n on the outside kind of messes up the geometric series idea. I don't think the e to the power affects anything. I think we're still just gonna get, or at least since I fail to see any simplifications that we can get with this. So my gut is telling me that We just have to worry about where cosine is 0 and we're okay.
So you're going to say they're all just simple poles.
Yeah, and this is the one where we think there was a typo. Where I'm not sure what the strength is for 1 or -1, but...
Oh, yeah. Oh, that's right. I found 2 typos, and I only told you about one of them.
Was this the other one?
No, I forget where the other one was.
Oh, okay. There's no, they don't know if like the powers of 2 should have been negative or something.
I want to say there was another negative sign somewhere that they screwed up.
Oh, okay.
Yeah, I didn't notice it while you were going through the chapter. So if I find it, if I see it again later, I'll put a note of it in Discord.
Okay.
Because I don't remember where it was right now.
Does it change the strength though? I don't know how we find the strength here. NTR, yeah. Hmm. We could take their result, like the very last line. And then plug it into the series for E. Where's my snipping? So if we... Wait, what was my idea? This is equal to tangent. So we could say that e to the tan z is the sum of 1 over n factorial minus 1 over... Wait. It'll be... Yeah, okay. Pi over 2 plus m pi plus a third. And so I was hoping maybe it wouldn't be impossible to just write out the first couple of terms of this series. Is the thing that I'm hoping. Hey, Megamorph. Am I feeling 1 over cosine z today?
I don't know.
Oh,
sexy.
Nice. I am. I feel like it's been a minute since I've seen you around, Mega. I hope you've been doing well. Okay, so if I just say when n equals 0, Is that just one inside these big parentheses, or do we have to worry about an infinity to the 0 situation? I guess we're never...
Yeah, I don't know. I don't know.
I don't know what to think about this. I'm just gonna not think about it too hard and say that the first term is 1.
Yeah, let's say it's 1.
Minus 1 over z minus...
Feels like it should be 1 because 10 goes to 0 and then e to the 0 goes to 1.
Minus 1 over z minus... This would mean that the negative terms go off to infinity, though. So we're getting significant change here, I think.
Oh, really?
Because, like, that 1 over z is going to get squared. So, did we...
Yeah.
Huh. Do we find an essential singularity?
Maybe.
Is this odd? It is.
Do they have answers to odd ones?
Yeah.
Okay.
Huh. That's so weird. Well, it's even going to change the location of the singularities, I think, right?
Really?
Or like the pi over 2 plus m pi things are going to get squared also. I feel like there's something weird with this. It would be great, Destin. This is the way the book was doing it, at least. Just looking at the series. I don't know. I feel like there's something that's wrong with what I've done here. I don't know what it is, but I feel like the argument of E is entire, so we don't have to worry about tangent. That feels better to me.
Yeah.
But I don't really know what's wrong with what I did.
Well, I don't know. It's not necessarily wrong, is it?
I guess I don't know what to think about it. They seem like there's some essential discontinuities now with that work, but I don't even know what to think about it. Well, maybe they're just poles still. No, I don't know. Is it if I check the answer on this one?
Yeah, sure. Sure.
Okay. Chapter 3, 3.5, number 1.
Let's see if we got part A right, too.
What? Oh, wait, no, for B. They are essential singularities. Oh my god.
Essential. Oh, they're all essential?
And Z equals infinity is a cluster point. So I was right with the second thing I said, at least. Part A, Z equals 0 is removable. Z equals infinity is essential. Okay, we did get part A right.
So so putting that up in the exponent of z changed the poles into essential singularities.
Yeah.
I mean, I think then I would say what you just did down here is right.
Yeah. I think
Because
so.
like you said, if you keep going to like n equals 0, 1, 2, if you go to 3, 4, 5, you're going to get higher and higher powers of z in the bottom, aren't you? Yeah. And that's our definition of essential singularity. Yeah, it's like where you can never go far enough to get all the z's in the denominator. They just keep going.
Yeah.
Yeah, we didn't think about infinity. I guess it makes sense it would be a cluster because they said, no, wait, what did they say in the chapter? They said
Oh, for just tan 1 over z.
tangent of 1 over z. Isn't
Yeah.
that what it was? Tangent of 1 over z?
Yeah, that's a cluster point at z equals 0. So,
Oh, so if we let z be 1 over t, we get basically we get e to the tangent 1 over t.
yeah, exactly.
Oh, well, that kind of makes sense that would be a cluster, I guess.
Yeah, I feel like we could kind of see that these are, well, I was getting so like there's something with these singularities are moving, like they won't be evenly spaced quite the same. It's really hard to see that from the series, but is Picard theorem useful for finding them? I don't know how you use them to find them. Okay. We're at the 2-hour mark. I'm just looking at the other questions that I had picked out. Show the functions below are meromorphic, and then discuss the analytic continuation of a function. I think we might just, or since we are at the 2-hour mark, I think I might rather just call it here for the reading group.
Yeah, okay.
I was looking at the links for chapter 4 of these sections, and chapter 4 is pretty beefy.
What's chapter 4? Is it residues?
Yeah.
Yeah, okay.
So wait, if it was just the first 2 sections, like we've been doing it 2 sections at a time, how many pages is that? From 206 through 235. 29 pages.
Sounds good.
You're up for it?
Yep.
Okay.
I actually really like residues. It's I do remember it being one of my favorite parts of complex analysis.
Okay, I guess let's go for it.
Yep.
Okay, sounds good. All right. Well, thanks for being here.
Yeah, sure. Thanks again for running it.
Yeah. And I'll see you next time.
Yeah, you'll see me for the dreaded relativity.
Oh, yep. More chapter 8.
Yeah. All right. See you, Don. Take care.
Bye. Okay. get music going, and then I'll switch over the info. Answering math questions from chat and studying. Bam. Okay. All that stuff is up to date, I think. Take down the pin. Remember to do that for once in my life. Wait, that's not what I meant to do. I meant to do that. Complex analysis reading group. Notes for 3.3 and 3.5. Next week, we'll work on chapter 4.1 to 4.2. I'm planning, I didn't say this to Fembox, but for the reading group, I only want to go through chapter 4, so theoretically there's only 2 more weeks of this. Okay. Damage chat, how's the rating? It was good. I do like being able to just like talk through problems with people. Guess already. Why stress as F has a central singular rate, some D cut out. Right. Okay. I think I'm just gonna continue with complex studying. I was reading through what was happening in the math discussion, but I think everything in there got answered? Question mark. Okay. Oh shoot. I skipped over your joke, Mega. essential singularities are like essential oils. You should just ignore the people who talk nonstop about how you need them in your life. They are essential for a reason. I'm just trying to catch up with chat. Just Destin and Mega talking though. It's not a scheme. That's what the space be called. Okay. Emma de Blam. Yeah. Been trying to learn it. Now, C was a doozy. I think F is gonna be even worse. And honestly, I kind of like the look of H as well. Oh, good, Papadoria. I saw that something had happened there. I'm glad that Cytos was able to help you out with it. Oh shoot, my mic is picking that up. I'm sorry if there's background noise. Uh, someone is doing some work on the house, I think, or something. Man, that's been going on for a while. I only just now realized that my mic was picking it up. I'm sorry about that. Okay, what's the series for log? I should know this. Let's, I guess, derive it. -1's the end. That's a good start. um... Oh, it's that? Yeah, I'm missing an alternation in here, aren't I? Organic Irish chicken smoothie. Yeah, oh, thank you. No worries. I appreciate you even stopping and saying hi. I should just look this up. Uh, hey, Najaf. I was doing it. Well, wait, where's the alternation? Oh, that's for 1 plus x. Okay. Oh, I get it. I get it. I did it right. I just didn't do it for the thing that I wanted. I should have been doing it with 1 plus C. And that changes what the series is. Okay, I think we're in agreement, Emma Demlam. C should equal 0 because if Z equals 0, we get 0. Okay. Sounds good. I should be playing Daisy either tomorrow or Friday. I'm not sure yet. Well, all-nighter, there's a thunderstorm, they cut the electricity. Oh no, Najaf. Organic Irish chicken smoothie is one name I've yet to stumble upon until now. Yeah, it's always an attention grabber when I see him pop up in a chat. Okay, so that's our series for log 1 plus Z. Oh. It's not as simple as saying replace Z with Z to the 1/2, though. Right? We have to replace the entire argument inside the log. Huh. Oh. Oh. You know the definition of essentials? Singularity. Hell yeah. I feel like this is not helpful. What, who even are you, log? Hey, Viv. Hope you're good. Hope your family's good. Does it grab attention? Yeah. Hope you have a good day. Organic Irish chicken smoothie. I like saying the entire thing just to like give it its full glory. Your old lecture from uni would be so proud. No skills are for the weak. Don't have paper to make their point. Log this challenge for future reference and documentation. True. Natural log it. Man, it's the natural choice. Okay, you know what? Erase all record of me working on that problem. What about G? So we square it if the magnitude's less than 1. Square it and invert it if the magnitude's more than 1. So exactly at 1, I do expect, or, you know, these things should be equal. Not necessarily analytic across there, but how do you figure that out again? Like if these, I guess if this is the analytic continuation. Well, no, the analytic continuation of z squared is just z squared. So, okay. What am I talking about? Okay, so we definitely have a double pole at z equals 0. I hope that's pretty clear, right? For z squared, that's a double pole at infinity, right? Wait, I'm reversing this. 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 Guys, do you know that I'm reversing it? There is no pole at 0. There is no pole at infinity. There is no spoon. I think you reversed it. So the only thing we have to worry about is this boundary point. Or the boundary, I guess. Reverse it, back that maths up. Put your thing down, flip it, and reverse it. When in doubt, do pen flipping. You remember reversing this? Good clip. Math does dawn. It sure does. Am I The only thing we have to worry about. So wait, is a singularity not defined or not analytic? I feel like I should know the answer to that question already. Not analytic. Okay. So can we check with Cauchy-Riemann? To be honest, I nearly made the same mistake. I think in other contexts it is just not defined, just complex. Well, actually, what's a singularity in another context? I don't know. How can we check analyticity? Wait, no, I already said it's not analytic. Because the analytic continuation of z squared outside the unit circle is still just z squared. So I think we have to have a removable discontinuity? Question mark? Or a removable singularity? I don't know if it's removable. There's no simple thing. Daisy is waiting for me. Don't tempt me. Branch? I don't think it's a branch. I think it's a cluster. Well, if we look at polar form, c squared is equal to r squared e to the 2I theta. 1 over z squared is equal to 1 over r squared e to the minus 2I theta. So when r equals 1, these are not the same at every point, right? Oh, wait. Can you be assistant to the branch point manager? Oh my god. You sure can. The isolated zero theorem to conclude that this function is not analytic. Really? Senpai? I'd never used it. I bet you that Phobos is, if you never catch her streaming. Um, I haven't used it for myself though. Or if you have a screenshot that you can like post or something, or I don't know, like I might be able to figure it out anyway too. I don't know. Try to cook with it, and you fail. Oh no. Uh, isolated zero theorem. How do we use the isolated zero theorem here? Isolated zero theorem. Because I don't think the book says it exactly. It just kind of says it indirectly. Yeah, right. Like the analytic continuation is unique. And the analytic continuation of z squared is just z squared. That's how I was thinking of it. Is that a good enough argument as it is? Well, no, because it doesn't help me classify it, right? I don't know how you classify it. Trying to approximate f of x such that f of x is equal to e to the x. Oh, so like a functional square root, I think that's called. Figure out how much of a ball ache CA is. Uh, it's kind of cool, but it's there's some kind of tricky parts. Tried something at SMO, ended up getting gnarly good approximations for LN2 and LN3 somehow. uh, I feel like that would be if you want a function f such that this is true. Is it like asking? I guess it doesn't have to be of this form, but like, what if it's just an exponential, or wouldn't it have to be an exponential with some other base? I don't know if this is a good thing or a bad thing, but like, can we solve that for A? Probably not. I don't think we can. It's in the power series. Oh, I guess you could get the power series for that, right? Yeah, I guess I think I agree with that color cone. I just don't know, like, what would you call this singularity? That's what I'm struggling with Because, like, it's continuous there. It's just not analytic. You don't think there's a name? Okay, because yeah, it doesn't really feel like a singularity in the same sense that other things are, but like, at least the book says that a singular point is where it's not analytic. I don't know. The mass stack exchange on function. Oh, hey, thank you, Papadoria. Emil Williams said a to the x is a to the e to the x ln a. True. Still annoying. It has solutions, but for all x. Wasn't that even better than what you were doing? Were you looking near 0, right? You'll get a formal power series, but it's essentially impossible to prove it has a non-zero radius of convergence. Feels bad. Oh god, if you have to go to math overflow, oh no. Dude, math overflow is insane. This formal power series does not converge. Dude, have you just looked at math overflow before? It's insane. This is where you go to do like math that no one has ever heard of. Properties of whitehead doubling for knots? Like, isn't a whitehead like a pimple? Yeah, exactly. I remember like a long time ago, I played a game with chat where you take two true titles from Math Overflow and you make one up, and the other people have to guess which one you made up. That's an insane game. What the hell is that symbol right there? It's like a smiley face without the eyes. Like that thing. I think it wasn't converging the method. I did solver coefficients, I got logs. Oh, okay. Right, it was a mathematician. Oh, okay. Cup product? It's a new one for me. Oh, of course he's bald. I feel like if that's your last name, you're like destined to become bald. That might be the wrong Whitehead. Oh, okay. He wrote a 3-volume. Is it Principia or Principia? I feel like I've heard people say Principia, but I want to say Principia. With his former student Bertrand Russell. Recognize that name. Wait, what was Newton's book? I don't remember. I like the duel of that guy called the cat product no cap. Maybe, Mega. But yeah, no, the site is for insane, like, PhD level math. It's kind of amazing that they're able to get answers. I guess a lot of these aren't being answered. But as from what I've heard, they're really mean to people who aren't like PhD level unqualified to answer these questions. Which, I mean, oops. I kind of get, but like if you make a mistake, they're not going to show you mercy. John Henry Constantine Whitehead. Interesting. Not bald. I mean, nah, he's losing his hair. This is just an old photo. Look at this and tell me he's not destined to go bald. Okay. If you're not Terrence Tao, you can't ask a question. That's what it feels like. Ultra filter. Yeah, and anyway. What were we doing? If you do ask questions here and tell my answer, true. Actually, is he on Math Overflow? That seems like a thing that he'd be on, I guess. Ooh, cool. So for G, I guess no singularities. Question mark. But not analytic on Z equal 1. Okay, the last one I want to look at from here was H, or H, as our friends across the pond say. Equals 1 to infinity, Z to the n factorial over n factorial. Just kind of looked funny. What do we do with you? Well, there can't be any poles, right? Isn't this just a polynomial? It's where you ask a question when my smooth brain cannot understand what on earth is happening in the paper I'm reading. Can I explain polar form? Yeah, Ved. So, are you talking about polar form of just like regular Cartesian coordinates? Like, how do you, like, are you asking how you go from a point x, y to a point r theta? Or are you asking about polar form in a different context? Okay, well, I'm just gonna assume that you know nothing about polar form and explain it like that. I'm sorry if I explain something that you already know. But let's just take a random point in Cartesian coordinates. Cartesian coordinates are your normal x and y axes. So x, y, 1, 2, 3, 1, 2, 3. Okay. I guess I'm just gonna choose a point 2, 1. I was debating if I should choose a more convenient point, but we'll do 2, 1. So that's how we represent a point in Cartesian coordinates, just the x and the y. But we can also, I should really draw this bigger. Sorry, I want to redraw this because I just realized I'm going to want to. 1, 2, 1, 2, x, y. Okay, 2 comma 1. We can also represent this in polar form. And so polar form, you still need 2 values, but now one of them will be distance from the origin, r. The other value will be the angle it makes with the positive x-axis, theta, Greek letter theta. And we can figure out these 2 values using trig. So we can notice that we can make a line right there with the positive x-axis, and we get a right triangle here. The bottom of the right triangle is 2, because that's our x-coordinate. The side of the right triangle is 1, because that's our y-coordinate. And so now with Pythagorean theorem, we know that r squared is equal to 2 squared plus 1 squared. So r is equal to root 5. And now using trig, we can find theta. We know that tangent of theta is equal to opposite 1 over adjacent 2. And then we can take arctangent of each side. Oops. Is that unit circle? No, it's not, right? That's what I was debating if I should choose a nicer point for. Just plugging into a calculator quickly. 26.57 degrees. Although normally we say in radians, which I really should have chosen a nicer point. Dang it. I should have chosen a unit circle thing. I didn't want to, but I should have. Inverse form is, yeah, that you can do that too. It's about 0.46 radians. I did have a question. I was running research Shor's algorithm. I'll have to look up what that is. I can do that right after this. And so in polar form, we'd say that the point is root 5, comma 0.46, or equivalently arctan of 1/2. And so that's the basic process. We can make x and y generic coordinates and get the general formulas to convert. So the general formula to convert from Cartesian to polar is r squared equals x squared plus y squared. Maybe even better is to write it as r equals root x squared plus y squared. And theta equals arctan of 1/2, of y over x. You do need to remember that arctan sometimes lies to you though. And so you have to remember where your x and y actually are and fix the angle to match. So like if you're over in quadrant 2, you're gonna have to do pi minus your angle. So that's the one like caveat to remember with this formula. Reed, I can link you to a website in just a second. The formulas to go in the reverse direction, if you have polar and want Cartesian, are x equals r cosine theta and y equals r sine theta. You can find these by doing trig on this right triangle. So x, the bottom side, will be cosine of the angle times hypotenuse r, and then the y coordinate is the height of the triangle, so that goes with sine. So I hope that helps, Bed. Let me know if you have any questions about that. Okay, we're gonna look at Piggymaster / Papadoria's algorithm, and then I see Ved is typing something also for Reed. If you want to learn about U-subs, I would go to Paul's online notes and look at this page. And general, this site has a lot of really good stuff for calculus. So if you ever like a thing you want to learn about more in general in calculus, I would use this site. Theta is argument, right? Modulus is distance from origin, right? Conjugate is mirror image. Yeah, so if you're talking about like complex variables, you would take the negative of the angle. So if you have the point like 2 plus I instead, if you did the conjugate to do 2 minus I, this would be like an angle of theta below the x-axis. Cytos, is that linked to the... Oh. Let me see what you're linking Cytos. I plus or minus theta? Yeah, I think to compensate for the different quadrants. Oh, I don't know if I want to do that one, Cytos. I'm sorry. I saw you post it. Megalomorph, I just realized, replied to Piggy Master. So you're trying to show that if a relatively prime... If A is relatively prime to B... A will have finite order. Oh god, I don't know what Shor's algorithm even deals with. Maximum minimum from the derivative? Yeah, basically... Apparently I've looked at this before. The quick answer, Ved, is if you want to find the maximum or minimum of a function, well, let me say the critical point of a function happen when f prime x equals 0. Critical points could be maxima, minima, and sometimes neither, but it's rare. You can classify if f double prime, or if there's a critical point at x equals a, then it is a maximum if f double prime of a is less than 0, meaning that it's concave down. X equals a is a minimum if f double prime of a is greater than 0. Which means that it's concave up. If it's equal to 0, then you're in trouble and you need to do something else. But or if it's equal to 0, then you need to it's probably just neither. There's some edge cases where this doesn't work, but 99% of the time it does work. Yeah, so concave down, and sorry, Papadori, I'll look at that more in a second. Concave down means that the function kind of generally opens down. So like a parabola, I should have drawn a nicer parabola. This parabola here, f of x equals x squared, minus x squared. This is always concave down because it's always kind of opening down. Like it's a bowl that points downward. I don't know what exactly this function would be, but a function like this. Holy crap. Thank you for the bits, hard luck. Yeah. I was not looking at chat. You timed it well. Um, here on the left side, this graph is concave down, and on the right side, it's concave up. And so right at that transition point is an inflection point. Yeah, it's a cubic graph, so we could call it like f of x is x plus 1 times x minus 1 would probably work. I remember one time when I was streaming like way early on, her luck got me really good. Like I basically had a heart attack. That clip is probably around somewhere still. Sounds good, Ved. Sleep well. Horse dying in your Minecraft world. It does sound like that. He was doing like his impression of a pterodactyl scream. I forget what the context was in that clip. I don't think knowledge of short algorithms is really needed for the question we want to prove. Okay. If a and b share no common factors, prove there is some n where a to the n equals b times something plus 1. And we're sure that algorithm is pretty cool to research, though. The order of quantum algorithm that could break cryptography if implemented correctly. Okay. Well, and so what did Mega say? If a is relatively prime to b, a will have finite order. We've done quite generally by showing that units form a finite group under multiplication. Essentially what you can do a pigeonhole principle argument. Oh. I probably can't do that either. What's our constant? I guess small c. Work mod b and use Euler's theorem. No Shor's algorithm required. That's good because I doubt you can run a quantum algorithm by hand. What is Euler's theorem? Yeah. there's about 1,000 of them. Euler's totient function? Bruh. N and A are coprime positive integers. Consider the sequence of remainders by dividing the sequence a squared, a cubed by b. Since there are only b possible remainders, you will eventually get the same remainder. So a to the I equals a to the j mod b for some I and j. Then because a is invertible mod b, you can cancel. The thing that my small c might be an integer, or even just a natural number. Even then, this doesn't seem important. I see how this is basically like you look at that as the division algorithm. Or like the definition of division or whatever. Okay, so you know what? Get rid of all that. Who cares? Okay, so I'm with it all the way through here. A is invertible mod B. Oh, okay, yeah. You can always... You can always get it so that it's 0 mod B eventually, is what that means. If you're given some power of A, you can always find a different power of A that gets you to 0 mod B. Which means you're allowed to cancel. I didn't realize that implied that, but okay. Huh. Yeah, Pablo, I think this is just probably the answer right here. I'll paste it over into the Discord if you want to like have a copy of it. But I don't think I'm doing better than that answer. A invertible mod B means there is C such that AC... Oh wait, is 1? For modular arithmetic? I guess, oh, multiplication. I was thinking of addition. I don't know, this is some number theory shit. We don't like number theory here. So they need A and B coprime. Oh, to assure yourself that you can always get every possible result for mod. Number theory does leave me numb. Number, I hardly know her. Oh, stupid. Okay. Oh, this is so annoying. I can only scroll slightly too far up or slightly too far down. Come on. With Functor? Functor, I hardly know her. For per age, I feel like it just had this is just a polynomial. This isn't as interesting as I thought it'd be, I don't think. So, like, any polynomial just has a... Well, it's an infinite polynomial. Ooh. Okay, that's the issue. That's what makes this interesting. It's an infinite polynomial. Can we figure out that this is like some version of E? It's like E with some terms missing. A lot of terms missing. We can bound it above by E for sure. I don't think that does much for the whole singularity thing. I think this thing just behaves like E, man. I don't think it's that special. We're dancing, Dr. L. Coefficient behaving more like 1 over n. That thinks you want to groove? Depends on the type of math. Radius convergence is probably a 1. I guess we can look at the ratio test, yeah. Uh... Oh. That is a weird exponent. The root test? Okay. The absolute value, or the magnitude goes inside, I think, here. Well, probably too early to do that. What do I do with you? The root is 1 over n factorial? Does it have to match the power of the variable? I did not know that about... I guess that makes sense, because I was getting... Huh. I didn't realize it was still valid. I've only ever seen the root test with 1 over n, but I guess I never had this situation before. What do we do with this limit? What the hell? We probably have to squeeze theorem that limit somehow, right? I assume we can't really evaluate that directly. What's a good squeeze? What's the main squeeze? You don't... Oh, like, we only care about, like, that part of the limit there? I guess it comes out to be the same thing. Like, we just get the limit and then it's going to be multiplied by the z. I don't know. 1 over r, where r is the radius of convergence. What? Or what does this limit come out to be? It gives you directly the radius of well, I feel like you're ahead of me or something, or like I still don't know what the hell you do with this limit. Oh, okay. You haven't gotten that far yet? Yeah, so I know like we require this to be less than 1, but I just didn't feel like the time to actually say that yet. Um, change the variable to k equals n factorial. Seems like a good move. So if n goes to infinity, then so does k. They go at different speeds, but I assume we don't have to care about that. And then I guess we do some logarithm stuff. Or like e to the minus 1 over k ln k. And then we're gonna bring the limit up. That's the root test of the geometric series. It is? Oh, or no, not okay. More like a harmonic series, I guess. Which that would be bad. I'm just gonna ignore that piece. That it looks more like the harmonic series. If I L'Hopital's that, we get just 1 over k. And so that's going to be 0. So we just get 1. Okay, so we do get that the radius is 1. So if it diverges in 1 itself, there's no way that's going to work. So why bother checking endpoints? If it's going to shoot off to infinity at 1 or more. Hey, Bravo Snipes. Hope we doing well. What do we say about that? I mean, it's just not really... It's just not really defined out there. Hey, Xfret. I'm looking at part H. We just did the root test on that series. Yeah, I'm doing well. Bravo. So I found that the radius is 1. Well, Color Cone found it. I'm just along for the ride. And now I think about I'm trying to think about what this actually means, I guess. I don't know if there's really a singularity. It's just kind of... Is it a singularity? I don't know. Is it one of the ones where there... Is it a natural barrier? Like, there is no analytic continuation. Maybe that's what they're going for here. Maybe, like, everything outside of one is essential. How does the books... How does the book find the natural barrier piece again? Well, so they look at this series and say that there is no anal continuation outside of the unit circle. Oh, and they do it with a really weird argument that'd be hard to replicate. But I feel like that's they probably want. Oh, Cabeza, thank you for the follow. Yeah, right. They basically show that the entire unit circle are essential singularities. It is real, Cabeza, yeah. I do Daisy also, but like, yeah. That was a meme. Thank you, dude. Yeah, that's my shtick. I do math as like my primary thing because I'm actually good at that, and then I will also stream like Daisy and random games, just because I enjoy them. Oh my god, no! I feel like I'm pretty much always failing at Daisy. The last time I played, it was terrible. I got wrecked so hard. Guys off the chain with math. Z equals 1 is a singular point. See myself like Professor Fink from The Simpsons when he explains that Toys for Aiden says, you wouldn't enjoy it the way I do. That's fair, yeah. I feel a little bit weird about it sometimes because like I feel like the multiplayers in particular really emphasize like being able to get kills in like PvP, but that's definitely not my strength. Oh yeah, the lore is cool. Yeah, oh yeah, and seeing like the real life stuff that the buildings are based off. I don't know if I have this argument inside me. My gut is telling me that this is a natural barrier. I have no clue how to even start this argument though. Well, I guess you'd start by saying one is a singular point because it goes off to infinity. But then what kind of transformation would we do? Oh wait, it's 1 over n factorial when z equals 1. Wait, no, it should converge. Am I all wrong? Is this not a natural barrier? Because I forgot it's n factorial. That's a big difference. So hmm. I don't know how to think about it if like z equals I or something like that, but I think it definitely converges for 1 and -1. So it could have an analytic continuation. Ugh. Okay, it's definitely not a natural barrier. But I feel like as soon as we get out, well, if we get outside of 1, there's no, it shouldn't converge, right? Like, if the magnitude's more than 1, that is going to blow up pretty quickly. Could it be a natural barrier, but it's like an open barrier around the unit circle, not a closed barrier? I don't know how you would show that. Convergence on the boundary, we can just take the modulus. Okay. Uh, can we show... Okay, so let like r be greater than 1. I mean, I'm not really justifying it, but it... I think maybe it is a natural boundary, and it's an open... It doesn't include the unit circle, but everywhere around the unit circle. I think that's my answer. I want to check it in the back of the book. Uh, 3.5, number 1. H. Z equals 1 is a natural boundary. Okay. They don't say that it's included, but... Wait. A bound... That's not a jump. You are a lion. You are a lion. There's no jump? How do they define jump? Yeah. Not a lynx, but a lion. They are equal on C for the last one. G. This is G right here. We just kind of said, like, it's not analytic. Or like, it's not analytic across the unit circle. Yeah, yeah. It's piecewise, but they're equal to each other. Oh no, they're not equal to each other. Oh no. I thought the magnitude being 1. Never mind. I mean, you can have a piecewise function that's still continuous and differentiable. But yeah, the inversion changes the angle. Never mind, they are not a lion. Not in complex analysis? Oh, really? Suhas, what's your question? I'm probably going to wrap up the stream soon, but if you can let me know soon, I'll take a look at it. The CPs are the same or continuation. Continuous for all real numbers, but differentiable for none. That'd be a hell of a function. Weierstrass? Yeah, I'm sure that someone has made that function. It's also a fractal. Oh, a Fourier series. There needs to be infinitely spiky. Differentiable at every rational, not differentiable at every irrational. Oh God. I think that's probably possible. Amma de Blam. It's probably something terrible. I don't know. This is where my knowledge of math is really breaking down. Can you have a function that is differentiable at every rational, but not every irrational? That's in the right phrasing, but who cares? Is this the same question? What the hell? It's too much math. Did I just say that during a math stream? That's too much math. I can bring it back up again. I think that there can be no such function. It isn't f of p over q equals 1 over q squared. Zero if the input is irrational. It's different. Wait, how's it possible to be differentiable at irrationals? Ugh. Ugh. I don't... The more I think about it, the more this doesn't make sense to me. I don't know. We... I'm not good at this type of math. This one is kind of close. It's not differentiable, but it's continuous. Diam? Diam. Yeah, for this version of it. Because I don't know, if it is a thing that like there's an error there that between every a pair of irrationals there's a rational and vice versa. I feel like it just wouldn't be possible to be or usually. I know. I remember Slim told me, or we're working on. Oh, I forgot the name of the function is, but it's an example function that's continuous at just one point. At zero. There's a function, I forget what it's called. I don't know. My brain is kind of fading. Stars over Babylon. That's a cool name. Countable cloud function, the popcorn function. Dude, these names are so much fun. Yeah, I'm not sure. My brain is kind of fading. This might be a good moment to wrap it up here. I did just literally say that something is too much math for me during a math stream, so I feel like it's a pretty good indicator. Yeah, I think we'll wrap it up. So yeah, I'll cut the YouTube stream off here. On Twitch, we'll look for a raid. People here on YouTube, thanks for being here.